In Chapter 14, we learned that correlation was going to measure the direction and the strength of a straight line relationship. So regression always is drawing a line to describe the relationship. Regression is going to require us to choose an explanatory variable, but correlation does not. Also, correlation and regression both are strongly affected by outliers. So if your scatter plot shows strong outliers, you do need to be cautious of this regression line that the computer is going to find for you. Take a look here at the maximum 24-hour precipitation in inches compared to the maximum annual precipitation in inches. So for each state, they looked at the maximum amount of water that was ever rained in 24 hours and compared that to the overall annual precipitation. To think, is there a relationship between what you see in one day versus what you would see for 1 year? It's interesting to see what happens when we have Hawaii in our data set. Now, Hawaii being an island, has an awful lot of precipitation. They've had a lot of precipitation in a single day, and they get a lot of precipitation throughout the year. So Hawaii is this high outlier. And when we have Hawaii in our data set, the correlation is 0.510. So even though that's not particularly close to 1, it's still on the road to being closer to 1. But what is interesting here is if we actually take Hawaii out, the correlation drops to 0.248. So here our outlier made it look like we had a much stronger relationship than we actually did. And so sometimes when you have outliers, you see how much impact they can have on all of these calculations. So when you have an outlier, be aware that it can sometimes make a relationship look like it exists when it really doesn't. The red line is including Hawaii, and the dotted line is when we don't include Hawaii. So when Hawaii is in our data set, it makes us look like there is a positive relationship here. But because that outlier was so strong, when we remove it, we actually end up with this relatively flat line, which indicates that there's really not a relationship between a daily amount and the yearly amount. So with that in mind, we need to recognize that the usefulness of a regression line for predicting depends on the strength of the association, which is the correlation. So we're going to actually square the correlation to find a very important measurement for us to use. So the square of the correlation, which is just the correlation squared, you simply square the value for the correlation. It provides us with the proportion of the variation in the values of y. So it's telling us how much these y values are changing, and it's telling us that based on the least squares regression line. So that r squared gives us the proportion of the variation in y that's explained by this least squares regression line. If your r squared is low, then it means this regression line failed to capture the variation that's happening in your data. But if r squared is high, then it means that the regression line did an excellent job capturing the variation in your y values. So if there is a straight line relationship, then you are going to be able to describe some of the variation from this line, because as x changes, then we would expect y to change with it. So going back to our femur example, we had a low value there at about 41 and a high value at about 84. So the scatter plot here has a very strong correlation. It's 0.994. So it's very close to 1, telling us it's a very strong positive linear relationship. R squared, where we take 0.994 and square it, gives us 0.988. So what that tells us is that the variation along this line as femur length is pulling the humerus length with it, it accounts for 98.8% of all of the variation. So if you had 100% of the variation to be explained, the regression line captured 98.8% of it. So it did an excellent job. But sometimes if your R squared is lower, then it just means that the line did not do nearly as good of a job explaining what's really going on in the data. The last thing I want us to talk about is this question of causation. A lot of times people will see relationships between two variables, they'll see a strong correlation, and they'll want to put a causation relationship here. So take a look. The strong relationship between cigarette smoking and death rate from lung cancer. There's plenty of data that shows that people who smoke have a higher rate of lung cancer. But does that mean that smoking cigarettes causes lung cancer? That's a different question. Another thing that we can look at is the strong association between the availability of handguns in a nation and the nation's homicide rate from guns. In countries with more guns, there tends to be more homicides with guns. In countries that don't have as many guns, there tends not to be as much of a homicide rate from guns. But does that mean that access to handguns causes more murders? And this is the foundation of many of the arguments that people have about the availability of guns. So both of these are examples of looking at relationships that you can definitely see if you look at the data. But just because there's a relationship doesn't mean that one is actually causing the other. So cigarettes, if you pick up a pack of those, it says right there on the label that cigarettes cause cancer. So there's really no way to deny that cigarettes can cause lung cancer. It doesn't necessarily happen for everybody, but there's a strong enough relationship that we recognize that it is the cigarettes that are causing the cancer. But the gun debate is a little bit harder to pinpoint that causation. In fact, every time that we have a political debate, we often have this gun debate. Do guns kill people or do people kill people? You've probably seen something like that on a bumper sticker. So that's a much harder relationship to show causation. So why is it that the evidence for cigarettes and cancer is better than the evidence for guns and homicides? Well, we've got a few facts about statistical evidence for cause and effect that we want to recognize here. So how do we show that there is a causation relationship? It's really important for you to recognize that just because you have correlation doesn't mean that you have causation. So how do you establish causation? Well, the best way is to do an experiment. But unfortunately, we can't always do an experiment. Particularly here, we can't make people smoke cigarettes to see if they get cancer, and we certainly can't give people guns to see if the homicide rate goes up. That would not be an ethical experiment. So what can we look at instead? Well, if there's a strong relationship between two variables, that doesn't always mean that changes in one variable is causing the change in the other. So often, there is a third variable that's lurking in the background that's affecting these two variables. The best evidence does come from a randomized comparative experiment, but we just can't always do those. So the observed relationship between two variables could be due to direct causation. That's certainly a possibility. It could be a common response, and that's where this lurking variable influences both X and Y, creating this high correlation, even though X and Y really aren't the reason that you're seeing these outcomes. And then there's also confounding. So confounding is where there's a variable that we just can't isolate from the variables that we're trying to measure. And then an observed relationship can, however, be used for prediction without worrying about causation, as long as the patterns in the past data continue to hold true. So that's important. Even though correlation does not imply causation, correlation does let us know that prediction can be appropriate. So even though it is difficult to build a strong case for causation without experiments, it can be done. And so some of the ways that this has been done, if we look at the smoking situation, doctors have observed that most lung cancer patients were smokers. Also, observational studies comparing smokers and similar, if you consider things like age, gender, overall health, non-smokers showed a strong association between smoking and death from lung cancer. So here we have to ask the question, could it be explained by lurking variables that the studies couldn't measure? Was there maybe a genetic factor that predisposes people to both nicotine addiction and to lung cancer? In that case, smoking and lung cancer would then be positively associated, even though it wasn't the smoking, it was this genetic predisposition. So how do we overcome those objections? How do we establish causation when we can't do an experiment? Well, some of the things that we can use to establish causation is to see that the association is strong, that it's consistent. So it means that different countries, different subgroups are all experiencing the same outcome. And then higher doses are associated with stronger responses. So people who smoke more cigarettes per day end up with more lung cancer. That would be an example of these stronger responses. Also, the alleged cause is preceding the effect in time. So thing A happens, then thing B happens. That's going to give you more evidence for causation. And we can see things like this by looking at the men and women. So it turns out that men started smoking earlier, and they started smoking about, I can't remember exactly when it became popular, but from the time that men started smoking commonly, about 30 years later, men started dying of lung cancer. Women started smoking more a little bit later, and then 30 years after that, women started having the lung cancer. So since you were seeing the same lag time in both of the groups, that helps us see that it probably is the cigarettes that's causing the lung cancer. And then finally, does the alleged cause seem plausible? Have we done animal research? Have we done other research that supports this cause, and does that make it plausible?